In this lesson, we will delve into the error analysis of fixtures in Project 4, with a particular focus on the analysis of positioning errors. Positioning error is crucial in the application of machine tool fixtures as it directly affects the machining accuracy of the workpiece. We will learn about the concept of positioning error, its causes, and master the methods for calculating it. Additionally, we will examine real-world cases to understand how to minimize positioning error. I hope everyone can fully comprehend and master these topics. In the practical application of machine tool fixtures, error analysis of the fixture is a key aspect in ensuring the machining accuracy of the workpiece, with positioning error analysis being the core component. Let's delve into the detailed knowledge related to positioning error analysis. Positioning error and its causes. When a batch of workpieces is positioned in a fixture, the maximum possible variation range of the process datum of the machined surface in the direction of the process dimension is usually denoted by the symbol dW. It mainly consists of two parts, datum non-coincidence error EB and datum displacement error DB. The determination of whether the positioning error meets the machining requirements is given by dW equals JB plus DB is less than or equal to 1 divided by 3 times datum non-coincidence error. This refers to the maximum positional variation of the process datum in the direction of the process dimension caused by the non-coincidence of the positioning datum and the process datum. In actual machining, when the positioning datum and the process datum are not consistent, datum non-coincidence error occurs. The calculation method for datum non-coincidence error JB is as follows. 1. When the direction of variation of the process datum is consistent with the direction of the machining dimension, the datum non-coincidence error is equal to the tolerance of the positioning dimension, as shown in the formula. 2. When there is an angle between the direction of variation of the process datum and the direction of the machining dimension, the datum non-coincidence error is equal to the projection of the tolerance of the positioning dimension in the direction of the machining dimension, as shown in the formula. 3. When the positioning dimension is composed of a set of dimensions, the tolerance of the positioning dimension can be determined according to the principle of a dimensional chain. The positioning dimension tolerance is equal to the sum of the tolerances of all the component dimensions in this dimensional chain, as shown in the formula. Datum displacement error, dB. This is the maximum relative variation in the positioning datum in the direction of the machining dimension, caused by inaccuracies in the positioning pair, cos, when using the adjustment method to machine a batch of workpieces. Condition, taking the example of positioning a cylindrical surface on a V-block. The manufacturing error of the V-block and the dimensional tolerance of the cylindrical surface can lead to a change in the axis position of the cylindrical surface, thereby resulting in datum displacement error. Calculation method for datum displacement error. When the direction of variation of the positioning datum is consistent with the direction of the machining dimension, the datum displacement error is equal to the range of datum variation. As shown in the formula, when there is an angle between the direction of variation of the positioning datum and the direction of the machining dimension, the datum displacement error is equal to the projection of the datum variation value in the direction of the machining dimension, as shown in the formula. Here are some common methods for calculating datum displacement. 1. Workpiece using plane positioning, dB equals 0, 2. Workpiece using V-block positioning. When the angle of the V-block alpha equals 90 degrees, the result is obtained. 3. Workpiece using cylindrical pin or mandrel positioning, A. When the inner hole of the workpiece and the cylindrical pin or mandrel are in an interference fit with no clearance, the datum displacement error dB equals 0. B. When the positioning datum shifts in any direction, the datum displacement error dB is the maximum clearance in the diameter direction of the positioning pair, as shown in the formula. C. When the positioning datum shifts in a single direction, the datum displacement error dB is the maximum clearance in the radial direction of the positioning pair, as shown in the formula. Workpiece using cylindrical pin or mandrel positioning D. When a workpiece is positioned using a long positioning shaft, the clearance in the fit can cause the workpiece to tilt, affecting the parallelism requirements of the workpiece. The calculation of positioning error delta, D, requires a comprehensive consideration of both datum non-coincidence error delta, B, and datum displacement error delta, E. Generally, the formula for calculating positioning error is dW equals GB plus dB. When the directions of GB and dB are the same, dW equals CJB when dB when the directions of JB and dB are opposite. Let's deepen our understanding of positioning error calculation through a specific example. Suppose there is a part that requires milling a plane on a fixture. The process datum is the bottom surface, and the positioning datum is the side surface. The dimensional tolerance between the bottom and the side surfaces is 0.1 millimeters, which means JB equals 0.1 millimeters. Meanwhile, the manufacturing error of the positioning pair results in a datum displacement error, dB, equals 0.05 millimeters, and both are in the same direction. According to the formula dW equals JB plus dB, the positioning error can be calculated as dW equals 0.1 plus 0.05 equals 0.15 millimeters. Positioning error directly affects the machining accuracy of a workpiece. If the positioning error is too large, it can cause the dimensional deviation of the machined workpiece to exceed the tolerance range, resulting in scrap. For example, when machining a high-precision shaft component, excessive positioning error may lead to the shaft's diameter not meeting design specifications, thereby affecting the fit accuracy between the shaft and other components. Therefore, when designing machine tool fixtures, it is essential to strictly control the positioning error, ensuring it is less than 1/3 to 1/5 of the corresponding dimensional tolerance of the workpiece, where T is the tolerance of the corresponding dimension of the workpiece. This is crucial to ensure the machining accuracy of the workpiece. To reduce positioning error and improve the machining accuracy of workpieces, we can take the following measures. 1. Reasonably select the positioning datum. Try to make the positioning datum coincide with the process datum to avoid the occurrence of datum non-coincidence error. For example, when machining a series of holes, choose an already machined plane as the positioning datum, which is also the process datum. This effectively reduces the datum non-coincidence error too. Improve the manufacturing accuracy of the positioning pair. Reducing the manufacturing error and fit clearance of the positioning pair can lower the datum displacement error. For instance, by enhancing the manufacturing precision of the V block and reducing the fit clearance between it and the cylindrical surface, the datum displacement error during the positioning of the cylindrical surface on the V block can be minimized. 3. Adopt appropriate positioning methods. Choose suitable positioning methods based on the shape, size, and machining requirements of the workpiece. For example, for work pieces with complex shapes, a combination of positioning methods can be used to enhance the stability and accuracy of the positioning. In the aerospace manufacturing sector, the requirements for error are nearly stringent, with zero error being a fundamental requirement. This rigorous quality demand is inherited from the quality standards of the superior engineering projects during the acceptance of Shenyang No. 1 machine tool plant in 1955. Back then, Shenyang No. 1 machine tool plant set a benchmark for China's machine tool manufacturing industry with its excellent quality and strict quality control. In aerospace manufacturing, even a minor error can lead to significant safety incidents, so errors must be controlled within an extremely small range. When studying positioning error analysis, we should also learn this rigorous attitude and dedication to quality. In our future work, we must strictly control errors to ensure product quality. Taking the machining of aerospace engine blades as an example, the blades have complex shapes and extremely high precision requirements. During the machining process, the control of positioning error directly affects the performance and the quality of the blades. To reduce positioning error, engineers use high-precision positioning fixtures and advanced measurement technologies. They select the datum surface of the blade as the positioning datum and enhance the manufacturing precision of the positioning pair to ensure the accurate positioning of the blade during machining. By strictly controlling positioning error, the machining accuracy of aerospace engine blades is ensured, thereby improving the performance and reliability of the engine. In this lesson, we focused on the analysis of fixture positioning error in the project. First, we learned the basic concepts of positioning error, including datum non-coincidence error and datum displacement error. Datum non-coincidence error arises when the positioning datum does not coincide with the process datum, while datum displacement error is caused by inaccuracies in the manufacturing of the positioning pair, among other reasons. Next, we mastered the method for calculating positioning error, which involves determining the relationship between the directions of datum non-coincidence error and datum displacement error. We also discussed the impact of positioning error on machining accuracy and measures to reduce positioning error, such as reasonably selecting the positioning datum and improving the manufacturing precision of the positioning pair. Finally, we understood the ideological and political background of the zero error requirement in aerospace manufacturing and deepened our understanding of the practical application of positioning error analysis through the case study of aerospace engine blade machining. I hope everyone can further consolidate the knowledge learned after class and apply it to actual study and work.